So this rephrasing kind of gives us a better idea how this definition 2 is connected to this open set definition. Because remember, an open set is a set such that for any point in that set, there exists an open ball centered at that point, entirely contained in that set that we're claiming to be open. So now we're starting to see we've kind of squeezed out this notion of open sets out of this definition 2 here, and I think we're ready to start our proof that proves the definition 2 here, that assuming this to be true, then that implies that this is to be true. So let's kind of solidify what our goal is here. So our goal is to prove if U is open, and of course prove given definition 2 is true, prove if U is open, then this implies that the inverse image under F of U is also open. So if we just take U to be an arbitrary open set in Y, if we just take U to be any open set in Y, so let me do that. If we let U be any open set in Y, and if we're able to show that the inverse image of this U under the function F is open, then we've just shown that any open set in Y has an inverse image that's also open, and therefore we've proven what we wanted to prove. So let U be any open set in Y, we say it with confidence, we prove that the inverse image under F of U is open. And let's remind ourselves, there's multiple ways to show that a set is open. But let's just take the straightforward route. This would be the first route that you might take in an investigation, unless of course you might be inspired by something else, or you might see another route that makes sense to you. But at first glance, it makes sense to just show this set as open the old-fashioned way. That is, let's take any point in this inverse image of U. So let P naught be in the inverse image of U. So any point, or we're just taking an arbitrary point in the inverse image of U. Remember, if you want to show that a set is open, if we can show that any point in that set, that for any point in that set, there exists an open ball centered at that point that is entirely contained in the set that we want to show is open, then we've just shown that that set is open. So if we can show that there exists an open ball centered at P naught, which is again any point in this set, I just arbitrarily chose this point. It's just a general point in the set in the inverse image of U. If we're able to show that there exists an open ball centered at P naught entirely contained in the inverse image of U, then we've shown that the inverse image of U under F is open, and we're done. So let P naught be in the inverse image of U under F. We show that there exists an open ball centered at P naught, entirely contained in the inverse image of U, thus implying that the inverse image of U under F is open. So again, let's try to leverage what we're given. What are we given? Well, we're given that this definition 2 is true. This definition 2 is true. So let's try to leverage that fact. We know that given any point in the domain of F, and remember, the inverse image of a set in the codomain of F under F must be in the domain of F. So this set, the inverse image of U under F, is a set in the domain of F, namely X. So we know that for this P naught in this set, which is just another point in X, we know that there exists, well, we know for any epsilon strictly greater than 0, rather, that there exists a delta strictly greater than 0, such that if P is in the in the domain of F, and P is in the open ball centered at P naught with radius delta, that is to say that P has a distance from P naught strictly less than delta. That's saying the same thing. Saying that P is in the open ball with center P naught and radius delta is the same thing as saying that P has a distance from P naught strictly less than delta. So if P is in X and P is in the open ball centered at P naught with radius delta, then this implies that the distance from F of P naught and F of P naught and F of P is strictly less than epsilon. Now, that is to say that F of P is in the open ball centered at F of P naught with radius epsilon. That's another way of thinking about this, as we talked about previously. Now, how do we leverage this? How are we going to use this? We're going to somehow have to think of the image of P naught under F. Well, that actually turns out to work out very nicely in our favor, because check this out. By definition of the inverse image of a set, remember, the definition of the inverse image of U is equal to the set of all points X in the domain of F, in this case X, so all X in the domain of F, such that F of X is in U. So check this out. Since P naught is in the inverse image of U under F, then that implies, by this definition right here, that implies that F of P naught is in U. So check this out. It might not seem clear what we can do from here, but oftentimes it's kind of helpful to rewrite what we know. Well, we know that, or not even just rewrite, just think about what we know and what we can say about what we know and how we can say what we know in different ways, in multiple different ways. Well, check out how we can say this in a different way. We know that U is open, and we also know that F of P naught, the image of P naught under F, is a point in U, which is an open set. So therefore, there exists an open ball with radius, and I'm going to deliberately say that this radius is epsilon, and you'll see why I do this later. There exists an open ball with radius epsilon and center F of P naught, such that this open ball, which remember by our notation that we've developed earlier, F of P naught with radius epsilon, is contained in U by definition of the fact that U, or by definition of an open set. Remember, U is an open set. So we can make this statement. There must exist an open ball with center F of P naught, since F of P naught is in the open set U, that is entirely contained in U. And we're just giving this open ball a radius epsilon. But check this out. Check this out. By this fact here in blue, we can say the following statement. We know that given any epsilon strictly greater than 0, there exists a delta that satisfies this property. So, even for this epsilon, this is an epsilon strictly greater than 0 because the radius of an open ball must be a real number strictly greater than 0. So we know for this particular epsilon, there exists a delta by the fact that this is true. Remember, because we're assuming definition 2 to be true. So there must exist a delta strictly greater than 0, such that if P is a distance away, or if P is in X, P is in the domain of P, if P, or that's the first assumption we have to make. If P is in the domain of F, and P is a distance away from P naught, under the X metric, I haven't been writing that in, but we can assume that when we're saying the distance between P naught and P, then we're in the domain of F, and therefore we're talking about the metric that under the metric D sub X, which is the metric that we're defining for the metric space X. So we know that there exists a delta strictly greater than 0, such that if P is in the domain of X, then the distance between P naught and P is strictly less than delta. Again, by this fact, this implies that the distance under the Y metric of f of p naught and f of p is strictly less than epsilon. But what is this really saying? Remember our rephrasing way back up here. Remember our rephrasing. What can we really say about this? Well, this implies there exists a delta strictly greater than 0 such that if p is in the open ball centered at p naught and radius with radius delta, which is the same thing as saying this right here, because if you're in the open ball centered at p naught with radius delta, then you must be in the space that this open ball lives in, which is in fact x, and you must be a distance away from delta. You must be a distance away from p naught, rather, strictly less than delta. So if p is in this open ball centered at p naught with radius delta, then that implies this, which is the same as saying this fact right here, that the distance under the y metric of f of p naught and f of p is strictly less than epsilon. That's the same as saying that f of p, is in the open ball centered at f of p naught and radius epsilon. And this open ball, of course, lives in the the codomain of f, namely y. But moreover, we can be more precise with this. We defined this open ball to be an open ball of radius epsilon and center f of p naught that is entirely contained in U. It's entirely contained in U. And remember our definition of the inverse image of U. It's all points x in the domain of f, x, such that f of x is in U. So check this out. P, remember, I just rephrasing this thing in orange here. This thing in blue right below it is the exact same thing. It's just said in a different way that's geared towards proving what we want to prove. So check this out. If P is in this open ball of center P naught and radius delta, remember, this open ball centered at P naught and radius delta, this is a subset of X. So P is a point in X such that the image of P under F is in this open ball, which is a subset of U. So therefore, everything in this open ball is a subset is also in U. So therefore, since f of p is in this open ball, f of p must also be in U. So therefore, look at what we just did. We've shown that any point in this open ball of center p naught and radius delta is in U. We've shown that any point in this open ball of center p naught and radius delta has an image under f that's in U. That is to say, if P is in the open ball centered at P naught and radius delta, then this implies that f of P is in U. So check this out, but that's the same as saying that P is in the inverse image of U. And check out this. I just showed that any point in this open ball of center P naught and radius delta must be in the inverse image of U. So therefore, this open ball, check out what we can say. We can say the following, that this open ball of center P naught and radius delta is contained in the inverse image of U. So therefore, I've just found an open ball with center any point. Remember, we let P naught be any point in the inverse image of U under F. And I've just shown that there exists an open ball centered at that point that's entirely contained centered at that point, again, which is any point. So therefore, I've just shown that there exists an open ball centered at any point in the inverse image of U that's entirely contained in the inverse image of U, therefore showing that the inverse image of U under F is open. And we've completed the first part of our proof.